So we're going to turn our attention to the periodic table. We're talking about elements and all that. If most periodic tables will have the symbol of the element, they'll have the atomic number, which is the whole number, the number of protons in the nucleus of an element of that type, and then they'll have a decimal number, and that's what we're going to talk about today. I call it the decimal number. So like the decimal number for hydrogen is 1.00794. And bottom line, that's how much a hydrogen atom weighs. Okay? Decimal number for copper is 63.546. That is how much a copper atom weighs. Now we're going to have to talk about it's not pounds or grams or ounces. Actually, that's going to be AMUs, or atomic mass units. But that's how that works. And that's actually all we're talking about here. We talk about atomic weight, okay, how much an atom weighs, but we're going to have to do this funky averaging. And honestly, the reason for the funky averaging, it's not really funky, it's called a weighted average, has to do with the fact that, like, for instance, we're going to pick on copper, and there's two isotopes of copper. We talked about that. So one's heavier than the other. So you have to take into consideration the presence of both. And then also you have to take into consideration how much is the heavy one, how much is the light one. That's the weighted average part of it. So there we go. So average atomic weight is the decimal number. And it is, like I said, in atomic mass units. Now, I learned at AMUs, but I'm not so sure OpenStax might do this. Atomic mass unit, they just do this, the letter U. Okay? So how much does a copper atom weigh? 63.546 U. Okay? U and AMU, you're just going to have to live with it because I'm of the older generation and the newer generations coming through, okay? So those decimal numbers, average atomic weight for an element, we have to take in consideration all the isotopic forms that are present in nature, okay? And how abundant each of those isotopes are, the light one and the heavy one. Sometimes average atomic weight can be called average atomic mass or atomic mass. They all mean the same thing, average atomic mass. So this is where I mentioned that, like, for two isotopes, we need to know which one there's more of in nature. We call how much there is in nature. It's abundance. Okay. This idea of a weighted average is one you run into all the time in courses. Like in this course, your unit exams collectively, I think, weigh 40% of your grade in this class. That's the weight of those. Okay. The weight of your homework is like 10%. It's a lighter weight. Okay. The final analysis, and actually Canvas does this for you, this calculation, is whatever grades you get on your unit exams, which I hope you do great, that weighs more than whatever percentage you get on your homework. It's a weighted average. So, yep, AMUs, some texts use, instead of AMUs, it's U, right? So we've been talking about standards in here, and we all have to be on the same playing field in science, because science is international. So it all goes back to actually one isotopic form of carbon, carbon-12. If you were to have, one carbon atom, which, man, it's hard to isolate one atom, anything, including a carbon atom, it would weigh exactly 12 AMUs. We talked about this before, just for kicks. Let's kind of, so one carbon-12 atom. This is the nucleus of my carbon-12 atom. How many protons are in there? What do you think? 6. Yep. Okay. If it's neutral, how many electrons are there? Also 6. Yep. I'll just kind of put electron cloud out here. You got it. Now, the fact that it's got this is the mass number we talked about on Friday, the fact that it's got a mass number of 12, and this is protons plus neutrons. How many neutrons does it have? 6. Yeah, I'll go ahead and make these little zeros. And it's kind of fun because by definition, that's a carbon atom. It weighs exactly 12 AMUs. And didn't we say that these subatomic particles, each plus weighs about 1 AMU? That's a proton. Each neutron weighs about 1 AMU. So to me, I mean, this isn't so surprising. Oh, this is 12. I mean, it's not like, it's just kind of nice. It's like, oh, that makes sense. How much mass do electrons bring to the table? Not much. Physicists would disagree, but chemists are like, they're massless, okay? They're very important, but they don't bring mass. All right. So you guys have used equivalency statements as ratios, what we call conversion factors. So we have this important relationship between an atomic mass unit, one cute little AMU or 1 U, okay, and grams. And here's the relationship. You don't have to memorize that one. And by the way, I say equals, but it's an approximation. So there is uncertainty. This is exact, the one is exact, but the 1.61 times 10 minus 24th, there's 4 sig things there. We could actually then, if you're into such things, we could take the inverse or the flip of 1.661 times 10 minus 24th, and you get 6.022 times 10 to the 23rd, which some of you guys maybe remember that's actually Avogadro's number, exactly. Now this relationship might be, I don't know if you have to memorize it, but it's a good one. So exactly 1 gram is approximately equal to 6.022 times 10 to the 23rd AMUs. So which is bigger, a gram or an AMU? A gram is a lot bigger, yes. So, cool. Well, people that are tasked with such things, I just wonder what sort of scientist goes out and does these things. But I mentioned copper, and somebody needs to go out and find out in nature, and it's a statistical thing. This whole idea of sampling is just crazy. So they need to get a representative sample of copper in nature, and they need to say what % of copper is the heavy one, what % of copper is the light one. And we would call that the % abundance. So what they do, what we know about percents or parts per 100, what they do is down here, this is like the number of atoms in your mixture, okay? And the top is the number of atoms of a particular isotope. So you take the number that you got of your isotope of interest divided by the total number of atoms that you sampled times 100, that will give you parts per 100. So percent abundances. So hopefully we're okay with this because we talked about this on Friday. That little superscript, so what is that little superscript 63 and 65? It's the mass number. It's the mass number, yep. The difference between mass number and atomic mass is a subtle thing. So mass number is counted. Mass numbers will always be whole. And atomic masses are the decimal number. Yep, but they can be kind of approximate sometimes. Okay, so somebody did their homework and they said of this would be what, the lighter one? You got 69% about of the lighter one, about 31% of the heavier one. Okay, this would be kind of like the lighter one, let's see, how do I say this? The lighter one would be like your exams, okay? I don't know. The heavier one would be like your assignment. Okay, so which one weighs more? Okay, so this is represented in Mother Nature. If we were to, instead of 100, if you have 100 atoms of copper, 69 would be the light, 31 would be the heavy. If we move the decimal place over, let's see, instead of 100, if we have 10,000, move the decimal place over, that means that you would have 6,909 of them would be the lighter one, 3,091 would be the heavier one, just another way of looking at it. So that's what that means. Picking on some elements. Now, most elements are not like hydrogen, but hydrogen's got its kind of own little history. Hydrogen's a very important element. It's the most abundant element in the universe. Hello. It's the simplest element, has 1 proton in it. Up here I'm showing 3 isotopic forms of hydrogen. And again, most different isotopic forms don't have their own name, but hydrogen does. Deuterium is hydrogen that has a mass number of 2. Normal hydrogen has a mass number of 1. Let's think about that. If I look at a hydrogen atom, I just get so excited about this. If I look at a hydrogen atom, how many protons in the nucleus? 1. Okay, and if it's got a mass number, which is A, right? Mass number. Okay, so that's the protons plus the neutrons, and it's equal to 1. How many neutrons does it have? 0! Isn't that awesome? It's just a proton. Most hydrogens are like that. They have no neutrons. Deuterium has 1 neutron. How many neutrons does tritium have? 2, exactly. Now I've got some little asterisks down here. I think they're just not very common. How uncommon are they? Here you go. Here's their natural abundances. So for normal hydrogen, which is a proton, no neutrons, looking at 99.985% in normal hydrogen. Deuterium, 0.015. Tritium, it's not, I think this is right. It's not a naturally occurring isotope of hydrogen. Doesn't mean it can't be made and can't be used. Can't be harnessed. Okay. Let's see. Let's pick on. Oh, by the way, then over here. So we talked about the mass number is here. It's an integer. It's a whole number because we're counting protons plus neutrons. But the atomic mass, or the mass of an atom of that type of isotope, is the decimal number. Okay, so how much it weighs? That. Boron, 2 naturally occurring isotopes. Then we have how much each one of those isotope weighs. We have the light isotope. So boron's atomic number 5. I think we looked at it on a picture the other day. So this one has what, 5 neutrons. This one has 6 neutrons. Okay. Which one's more abundant, the heavy or the light one? The heavy one. Yep. The heavy one's up 80 versus 20%. So can you see where the weighted average, we're going to do some calculations like this, but can you see where what we see on the periodic table is weighted over towards the heavy side because it's more abundant. So instead of being like 10.5, which is the average of 10 and 11, okay, it's 10.81 because the heavier element's more abundant, or excuse me, the heavier isotope is more abundant. Neon, 2 naturally occurring isotopic forms. Wow, which one's more abundant, the heavier or the lighter one? The lighter one's a lot more abundant. So if we look at what the number, and we're going to see how we get these are what you see on the periodic table. How do we get that? You can see it definitely favors 20 instead of like 20.5, which is the natural average between 20 and 21, 20.5. It's like, nope, because there's not much of the heavy one. Magnesium, 3 isotopic forms. And yeah, the first one, the lightest one, is the most abundant. So these captions, A, B, C, D, kind of go with these pictures. These are if, and some of you guys recognize Avogadro's number. We said that, what did we say, 1 gram is approximately equal to 6.022 times 10 to the 23rd AMUs. That, of course, is 1 mole. We're going to get to that here in a minute. But if we have the same amounts, which is 1 mole, if we have 1 mole of fluorine atoms, the fact that they're all the same color says that there's only 1 naturally occurring isotopic form of fluorine, mass number 19. Chlorine, we should see 2 colors there. But can you see where the blue ones are present in only about 25, 24%? Pure blue ones. This is just to kind of visually to see. If we have 1 mole or 6.022 times 10 to the 23rd magnesium atoms, oh, we picked up a 3rd color. There must be 3 isotopic forms of that. You kind of see how that goes. 4 isotopic forms of lead. Ooh, what's that yellow one? The yellow one goes down here, 1.4%. So you can kind of see what that would visually look like. So how do we get those decimal numbers, those weighted averages, taking into consideration how much we have of each isotope? The other thing is, and it was on the column we looked at a little bit before, we need to know how much does an atom of that particular isotope weigh? So what we do, we looked at the summation, that Greek letter sigma, okay? In math, that means to sum. So basically, for every isotope, what we do is take how much it weighs, that isotope, and we multiply it by what we call its fractional abundance. And I have a slide coming up. The deal with fractional abundance is that is just the percent abundance divided by 100. So if you have percent abundance, you got fractional abundance. So you guys used the summation the other day when you came up with your standard deviation, your average standard deviation. So here's what it would look like. Okay, so let's say we had one isotopic form. Well, we'd stop like that. If we have two isotopic forms, it would look like this. For the second isotope of that element, we'd have to go out and see how much it weighs, and then we'd multiply by its fractional abundance. Say if we had 3, we have 4, okay, etc. However many there are. And then we're going to add those together. So we'll do an example. But again, don't let it throw you off in that little formula. The fractional abundance is the percent abundance divided by 100. That's it. So here we go. Let's pick on copper. So we have copper mass number 63, copper mass number 65. Which one's more abundant? The lighter or heavier? The lighter one. Yep, the lighter one's more abundant. So when we apply this formula, you're going to come up with the lighter one. It's going to be our mass, our decimal mass is going to be closer to the 62.93 than it would be the 64.9. Okay. This last column is how much an atom of these different isotopes weighs. Now, yeah, I think especially in biology, I'm not sure, but we tend to kind of take its mass, its weight, and use it as its mass number. But this is protons and neutrons, and this over here is AMUs, how much it weighs. But it kind of works a little bit, because notice what this number rounded to two digits is, 63. The 64.928 rounded to 2 digits is 65. So that's kind of where that comes from. But they're different. Okay, so we're going to have two terms added together. So we pick on the first isotope, the copper 63. We have to jot down how much it weighed. That's that last column, the 62.930 AMUs. And then we have to, for that isotopic form, jot down its fractional abundance, which is its percent divided by 100. And then we need to add it to, we turn our attention to the second isotopic form. So we're going to add that to 64.928 AMUs times the 30.91 divided by 100. And when you do that, you know, I've really stressed rounding, and this is some of my least favorite. How do you round is like this, where you have addition, clearly addition, but you also have multiplication. And the way it works is, how does it work? There's definitely uncertainty in the weights and uncertainty in the percent abundances. So I'm going to tell you later what the rule of thumb is, but if it's something that's heavier than, I think I say, something that's heavier, boron or heavier, basically for this type of problem, give me 2 decimals for this sort of problem. And that's generally what we say justified, so 2 decimals. If it's, that just leaves beryllium, lithium, helium, and hydrogen, then you'd probably be, in the information you're given, have to give me 3 decimals. All right. Now this is one of those unique chemistry problems, and I promise there'll be one on the test like this, that you can check. You can totally check. That number should match up with this number. Every once in a while they don't, because they've updated the periodic table or something. But to 2 decimals, I got 63.55 here. Okay, so this is one case where you can actually check your answer. That's kind of fun. Doesn't happen that much. So we've been talking about this. You told me the lighter one was more abundant. So that's why it's, if a simple average would be just what, 64. Between 63 and 65 is 64. But it's not a simple average, it's a weighted average. Okay, this one's a totally extreme. What was it, 99.99, like a bunch of the normal hydrogen versus deuterium. So that's why on the periodic table, you actually see it's way over there. So like the natural average would be 1.5. Well, this is 1.00798. Okay, so that's kind of, okay, so this part will be due, well, we're not meeting Wednesday, so bring it Friday. All right, so let's kind of ease into the next material. Oh yeah, I'm going to start this one out. First slide with a video, I hope, if it works. It's working. Yes, a mole. Mole. The origin of the mole. Why do we have to have a mole? And you guys have probably kind of hopefully committed this number to memory. If you haven't, you will for this course. But you need to memorize that 1 mole is equal to 6.022 times 10 to the 23rd. Now that's with 4 sig figs. A little bit ago, we actually saw it with 5 or 6 sig figs. 1 mole is equal to 6.022 times 10 to the 23rd of anything. What I started to say is the origin of the mole is the fact that atoms are so dang small. Atoms are small, molecules are small, most molecules are small. So in order to get something to sink your teeth into, you have to have a bunch of them. If I were to have water, just water. If I were to have some water, let's see. I don't know, it's pretty small. The volume about the size of your pinky. Then you have 1 mole of water molecules. Now don't forget what scientific notation means. Okay? 10 raised to the 23rd power means that I take this decimal and move it over here 23 places to unpack that scientific notation number. That's a big number. Okay? So, it's referred to as Avogadro's number. This kills me. This will slay me. So, you can abbreviate MOLE by MOL. Like, really? Thank you. Okay? So let's take a look at this video. Now, I did not preview this, but you can't draw donuts. I don't know. It could happen. Like the video said, why do we use a mole? So we can kind of talk about a parcel, like a mole of particles. So rice, I didn't bring the prop, but like you can hopefully kind of picture rice grains. Well, if you have a bowl of rice grains, rice is a very important staple in a lot of different cultures. You would have rice grains that would cover the land area, and we're like, oh man, is it 75%? I don't know. But anyway, there's a lot of the earth that's covered with liquid water, but the land area would be problematic because you're looking at 75 meters, 75 of these in rice. It kind of makes it hard to breathe to think of that. 1 mole of rice grains, that's problematic because you couldn't gather that many because even though it's a staple worldwide, there haven't been that many grains of rice grown since the beginning of time. Still with the rice grains, if you were to gather a mole of rice grains into one object and make that object a cube, it would be 120 miles on each edge. Mole of rice grains. Rice is pretty small. That's what a mole of rice would be. Switching gears, I always think of the Ghostbusters. If you have marshmallows, like the marshmallow guy. If you have a mole of regular marshmallows, it would cover the United States up to a depth of 600 miles. problematic. Then I think of like, I dream of Genie, where, can't remember his name, but he would always wish for just crazy things. So good thing he never wished for a mole or anything. Let's see what else we got. Snowflakes. The mole snowflakes would be cover the United States up to about 2/3 of a mile deep. If we were going to count a mole, like 1, 2, 3, 4, up to a mole, okay? If we were going to have everybody on Earth doing that, which would be crazy, it would take the number of people on Earth times 51,000 times the number of people that are on Earth at the time this was written, and they'd have to do it for 75 years continuously. This is probably outdated, but computer, you know, when you take programming, they have you like have a computer count, like 1, 2, 3, have a computer count. Well, if you have a fast computer that can do 1,000 millions of instructions per second, the same computer is so fast that it works, and those are kind of iterations. If the computer was going to do that and count up to the population of the Earth, it could do that, the United States, at the time this was written, it could do that in less than a second. The same computer, if you were going to have it you're going to do people do it, you're going to have a computer do it, okay, count up to a mole, it would take 1.9 million years for that to cycle through a mole. So 2.022 times 10 to the 23rd times. Hockey pucks would equal mass of the moon. Basketballs, I think the video might have said, problematic again. Like it says, you need to have another planet, mole basketballs. Okay. And this is one that the video alluded to also. If you were to, they had like a baby getting money, like $1 million or a mole of pennies. That's it. When they were born, that's a lot of money. Okay. This says that you could go ahead and divvy that up at the time this was written by everybody on Earth. Everybody get $1 million and everybody spend like crazy. Wait a minute. Have everybody get a mole of pennies. This is how many pennies you have, but you know how much money that is by just, it'd be like 1.5 times 10 to the 12 dollars. Does that sound right? And that's how many pennies. Everybody could spend $1 million a day, and you have 4,000 years worth of money. Okay, so I just have one slide from OpenStax to kind of say, well, why do we have a mole? Why do we introduce the idea of a mole? Because atoms and molecules are so dang small. How small are they? And this is from your textbook, and it says if you were to have a single droplet of water, it doesn't look like it, but there are about 100 billion times more molecules in there than are people on the Earth. So you're like, kind of puts the small into perspective. Another equivalency statement. Okay, so with every equivalency statement, we know that you can put one in the numerator, you can flip it over and do it like that. So we have two ratios that we can use as conversion factors. So 1 mole of anything, we're going to start with atoms. 1 mole of anything. We're going to stop being silly, not doing donuts, hockey pucks, basketballs. 1 mole of cute little atoms. Well, it means that you have 6.022 times 10 to the 23rd atoms. So these things with boxes around them, okay, these are our tickets to convert. Now, I told you, I tried to kind of tell you, if you have we took an equivalency statement, we have these two ratios. If we want to know what we can use it to convert back and forth between, well, we can use this to convert back and forth between moles and atoms. Okay, atoms and moles. Depending upon what units one can, so we'll know which version to use. By the way, while I'm at it, notice when I went up here, I said moles and atoms. Atoms and moles. Don't let I don't know, I'm not an English person. Don't let the phrase, or whatever you can call it, mole of atoms, mess you up. The mole's the important part. You'll see when you're doing this what I mean. So we're going to work 2 problems, and we're going to use those ratios to get down the road. So when I work these problems here on the next slide, the first thing is always going to be the thing I want to convert. So how many moles of atoms is 1 trillion hydrogen atoms? So that's going to be my first term. 1 trillion hydrogen atoms. The first term over 1, then go back to the previous slide, take one of those ratios, get from atoms to moles. That's it. Notice I put the phrase of atoms in brackets. This is to say that this same problem usually will not have those two words I have in brackets, will usually not appear. So it usually read like this: how many moles is 1 trillion hydrogen atoms? The other one we're going to work, what's going to be my first term there? Yep, that's going to be my first term. Yep. Now, does it have to be? No, I've seen some students that, for whatever reason, they don't do it like that, and that's fine too. So here we go. How many atoms is 0.555 moles? Well, we already know 0.555 is about a half. Does that seem right? So you're going to be about a half of this, about-ish. That's one. So you're looking at probably 3-ish times 10 to the 23rd. So it's kind of nice to kind of keep that in mind. I'm not real thrilled. I probably would do this. I would go 1 times 10 to the 12th over 1. Oops. That's a 1, not a 7. 1 times 10 to the 12th. This is kind of unusual. We're going to go with exactly 1 trillion hydrogen atoms. We're going to say there's no uncertainty brought there. That's 1 trillion hydrogen atoms. If you're like me, I have to concentrate. I'm like, trillion, what does that mean? Well, we have million, billion, and then trillion. So that's kind of how that goes. So a few slides ago, we had those two ratios. And I'm going to go left. Left is going to be A, right is going to be B. Which of those two ratios were we going to go with to make atoms cancel? Yep, she's going with 1 mole over 6.022 times 10 to the 23rd. And I probably, now we're indicating the element here. That's kind of optional. You know, 1 mole over 6.022 times 10 to the 23rd atoms. Atoms cancel. So I said that there's no uncertainty in this 1 trillion, so how many sig figs do we need to round it to? I see somebody saying 4. It's 4. Here's 4. And the reason for that is we're going 1 trillion is exact. So 4 sig figs, 1.61 times 10 to the minus 12 moles. Now, hopefully this seems reasonable. This is a small number, really pretty darn small number for having, you know, you figure it's got to be small because 1 trillion, 1 times 10 to the 12th, even though a trillion seems like a big number, it's nowhere near a mole. So this is reasonable. It's just called that. Does that make sense? Okay. So the first term of the next one is going to be 0.555 moles over 1. And so now what's the next term going to be? Yep, the 6.022 times 10 to the 23rd on top. 6.022 times 10 to the 23rd atoms over 1 mole. Perfect. So moles cancel now. Fingers. How many sig figs? I'm liking 3. Very good. And I said it'd be about a half a mole, and it is about a half a mole. 3.34 times 10 to the 23rd. I'll buy that. Any questions about that? So that's how far I wanted to get to today, which is great. Friday we're going to pick up with molar mass. And so when you come in Thursday to do lab and such, there'll be one calculation where you're like, you know, how do we finish up that calculation? And we'll go through it Friday. Meantime, anybody who's interested will go over to Chem Lab and see what we got going on, see if we can print and